Electromagnetic fields in different media. At lower frequencies, we can get away with thinking about electronics purely in terms of voltages and currents traveling through wires, like water flowing through a pipe. But when you move up into the microwave spectrum, the wavelengths become so short that they are comparable to the physical size of your components. The water in a pipe analogy breaks down. Instead, you have to start thinking about energy propagating as traveling waves of electric and magnetic fields interacting with the physical space and materials around them. To understand this broadly and deeply, we need to look at what materials, the media, are made of electromagnetically and how they manipulate these fields. The three pillars of a medium. Every material you will ever use to build a transmission line, design a filter, or guide a wave is defined by three fundamental electromagnetic properties.
Permittivity, the dielectric constant. Permittivity describes how much a material resists the formation of an electric field within it. In microwave engineering, we usually talk about relative permittivity, or the dielectric constant. Free space, a vacuum, has a baseline value of 1. What it does to the field? When an electric field enters a dielectric material, like the FR4 or Rogers board in a PCB, the molecules in the material polarize, aligning themselves with the field. This process absorbs some of the wave's energy to maintain that alignment, which fundamentally slows the wave down. The practical impact? Because the wave slows down, but the frequency remains the same, the wavelength shrinks. This is an incredibly powerful tool. It allows you to design compact filters and resonators because a quarter wavelength piece of transmission line is physically much shorter on a high dielectric board than it would be in the air.
2. Permeability. Permeability is the magnetic equivalent of permittivity. It measures how easily a material can support the formation of a magnetic field. What it does to the field. For most common microwave materials, copper, air, standard PCB substrates, the relative permeability is essentially 1, meaning they don't interact strongly with magnetic fields. The practical impact. When you introduce special magnetic materials called ferrites, things get very interesting. Ferrites can interact with a magnetic component of the microwave field in a directional way. This allows for the creation of components like isolators and circulators, devices that allow microwave energy to flow in one direction but block it from flowing backward, which is vital for protecting sensitive amplifiers.
3. Conductivity and the loss tangent. Ideally, we want our wave to travel from point A to point B without losing power. In reality, media absorb energy. Conductivity in metals. While we use metals, like copper traces, to guide the wave, metals are not perfect conductors. At microwave frequencies, a phenomenon called the skin effect occurs. The rapidly changing magnetic fields push the electric current to the very outer surface, the skin, of the conductor. Loss tangent in dielectrics. Insulators aren't perfect either. As the alternating microwave field rapidly flips the polarized molecules in the dielectric back and forth billions of times a second, molecular friction generates heat. The loss tangent measures how much microwave energy is lost to this heat.
Fields in practical microwave structures. How do these media dictate the behavior of the devices we actually build? It all comes down to the boundary conditions. What happens when a wave hits the border between two different media, like copper and air, or FR4 and copper? Microstrip transmission lines. Think about a standard microstrip line, a flat copper trace sitting on top of a dielectric board, with a solid copper ground plane underneath. The electromagnetic wave isn't just inside the copper trace, it's actually traveling in the dielectric space between the trace and the ground plane, and some of it is fringing up into the air above the trace. Because the wave is traveling through two different media at once, air and the dielectric board, it travels at an effective velocity that sits somewhere between the speed of light in air and the slower speed inside the board. Impedance and S parameters. The specific mix of media, the width of your trace, the thickness of the dielectric, and its permittivity completely dictates the characteristic impedance of that transmission line. Impedance, in simple terms, is the ratio of the electric field to the magnetic field in that specific medium. If your wave is traveling through a 50-ohm transmission line and suddenly hits a filter section that looks like 75 ohms, the fields cannot smoothly transition. Some of the wave's energy must bounce back toward the source. This exact interaction between fields and the media they travel through is what you are measuring when you look at S parameters, like S11 for reflection and S21 for transmission, on a network analyzer.
Waveguides. If you need to move very high-power microwaves or operate at extremely high frequencies where the loss tangent of PCB materials is too severe, you use waveguides. A waveguide is simply a hollow metal pipe. The medium is just air, or sometimes a pressurized gas or vacuum. The fields bounce off the highly conductive inner walls. Because there is no solid dielectric to cause molecular friction, waveguides have incredibly low loss. However, they only allow waves to propagate if the wavelength is small enough to fit inside the pipe's dimensions, acting as a natural high-pass filter. When the relative permittivity is 1, like in vacuum, the wavelength is long. When the relative permittivity is 10 times the relative permittivity in vacuum, the wavelength is much shorter. When the dielectric material is lossy, some of the electromagnetic energy turns into heat and lost permanently. Enjoying this? Smash that like button and subscribe for more RF and microwave engineering content. Drop a comment below with what you want to see next. I'm reading every single one. Let's get back to it. Thank you.